In this video, I want to use Gauss's law to determine what the field must be like inside a sphere of uniform surface charge. So let's start with a sphere that has a positive charge on its surface. We want to start by creating a Gaussian sphere whose radius is just a little bit smaller than the object itself. So the object has a radius of, let's call it A, and the Gaussian sphere, the imaginary boundary that we've created, has a radius of R. And let's say that R is less than A. Part of Gauss's law involves finding the charge enclosed by an imaginary Gaussian surface of our choice. In this case, I chose the red sphere that's just a little bit smaller than the object itself. So what is the charge enclosed? Well, in a conductor, many charges are free to move. And what they'll do is they'll spread out to the surface of the conductor because positives don't like to be near other positives, and negatives don't like to be near other negatives. So the spreading out of excess charge is a behavior that all conductors will exhibit. Since the charges are spread out among the surface here, that means that there's no net charge inside our Gaussian surface. The charge enclosed is actually zero, even if there's a substantial total charge on the surface. With this in mind, if we are to replace the flux with the field times the area, it can be shown that the field is going to be zero, no matter what the area of our Gaussian sphere is. So the field inside our object is zero at all points. This would hold true for any Gaussian surface. If the charge enclosed is zero, then the field inside that region must be zero as well. Now let's do a little bit more complicated one. Let's try one where there's a sphere of uniform charge density inside the object itself. Here, the excess charge is not just concentrated on the surface, it's all throughout the object. And let's say that our object has a radius of, we'll call it A. Now what we'd like to do is create a Gaussian sphere of our choice of an arbitrary radius, and I'll call that R. Let's say that our sphere has a charge Q total inside of it. In order to analyze this better, we'll use the concept of volume charge density. Volume charge density often has the Greek letter rho, and it's defined as the total charge divided by the volume of the object. Technically, this is an average volume charge density. It is possible for an object to have varying charge density inside of it. Like, for example, if you had more charges that were embedded in one location and less charge in other regions. Oh, that could happen. Now, what we want to do is we want to analyze our Gaussian sphere, and we also want to analyze the total sphere. Part of Gauss's law is finding out what charge is enclosed within your Gaussian surface. So if we divide our charge enclosed by the Gaussian sphere by the volume enclosed by that same sphere, that'll give us the charge density inside our Gaussian sphere. And we can do the same for our overall sphere as well. These two things are going to be equal, and the reason why they're equal is because our volume charge density in this situation is constant. So these things are going to be proportional to each other. If I rewrite the equation, I get this. The charge enclosed by my Gaussian sphere is a ratio of the volume inside that region over the total volume times the charge of the overall object. Now we have a formula for the volume of a sphere. The total volume will be given by 4/3 pi times a cubed. And the volume of my Gaussian sphere will be 4/3 times pi r cubed. If I just substitute those expressions in here, we'll get this. Finally, I'll use Gauss's law, that the electric flux through my red Gaussian sphere will be equal to the charge enclosed by it over epsilon naught. I'll replace the charge enclosed with this expression here. I'll replace the electric flux with the field times the area, because remember, that is our goal here, is to find out what the field is like inside the sphere. Alright, for our Gaussian sphere, the surface area will be 4 pi r squared. And we can divide. Notice that our r squared will cancel with 2 of the r's above. And we also want to recall that Coulomb's constant is 1 over 4 pi epsilon naught. With all those things in mind, we end up with this formula. our electric field inside the sphere of uniform volume charge density is going to vary linearly with the distance from center. So if I am to draw the sphere here and just put an x-axis, we find that the field at the center is naturally zero. The reason why is for every charge that we have to the left of the center, there's a charge to the right of that center. So the field contributions due to those charges would cancel out at the center. And for every charge we have above the center, there's an equal one below it. So it should make sense that the field is zero at the center. But we also showed that at this point, the field would be given by kq over r squared. If I make a graph of what the electric field is like, this is an important boundary. This is an important point because anywhere beyond that boundary, our field has the formula of kq over r squared, where r is the distance from center. But we also know that the field needs to be zero at the center, and it's going to vary linearly inside the sphere. E equals kq over a cubed times r. A is just a constant radius of our object itself. Let's verify that both of these formulas do give the same answer at the boundary A. So let R equal A. Do we get the same result so that they match up at that boundary point? They do match. So at the boundary of x equals a here, our fields have the same value.